Hello guys, welcome back to my channel. So in this video, I'll just be showcasing the small uh, parallel systems dispatcher that I've been working on as a replacement for the current one in Seaflake Engine. This one is inspired from Shred, the shared resource dispatcher, which is commonly used in Rust libraries for systems and task dispatching. But I thought that I want to implement my own, so I just decided to do that. Right. So yeah, let's get to it. So this is the basic interface, right? So you just have a simple registry. You don't have to worry about this. This is just for logging stuff. But you just have a simple registry. You can insert systems in it. So this is different from Shred, where you have traits that implement a specific execute function, for example. So yeah, this is just like my old Seaflake engine dispatcher, like the single-threaded one. So you could just insert systems that have a world reference to them, and from within that world reference, you can do like cool things like, borrow resources, either mutably or immutably, right? So you either do get or get mut, and that just borrows the resource in parallel. Since this is a parallel systems dispatcher that can run multiple threads in parallel. So right now I only have one system. You create a simple world. You sort the registry, since this also supports having do I say task injection? So dependencies, for example. So for example, I can have a task run after another task. So let's say system B must run before system A, something like that. You'll actually have to add the system B as well. So system B, like that. So this tells system A to run after system B, or I can make it so that it runs before that. And this is all handled using a topologically sorted graph afterwards, using the pet graph library. So you just have to sort the registry, and then you can build a simple dispatcher from that using a world and a number of thread counts to limit the number of threads. So if I were to execute the code right now, you would see that it does not compile, and that's because I forgot to save. If I were to run the code, you see that system B executes before system A, and that's what we told it to do. If I were to tell system A to execute before system B, that happens too. Now, these two systems can't run in parallel because I told them to execute in separate groups. That's how I handle dependencies. Basically, I just tell all systems if they have any dependencies like this, they just can't execute in parallel, which you simply can't do. Now, if I were to remove this constraint, these two systems will be able to run in parallel. Now, this happens because neither of these systems is allowed to borrow anything from the world. So for example, let's say I tell it to borrow a U32, which is basically just a resource, right? Since I have a resource trait that is implemented for any type of T, right? So I could just do stuff like that. So let's say I borrow a U32, I don't know, let's call it value, and let's debug it. Very simple. This would give me an error. Oh, I have to actually default reference it. This would actually give me an error since I haven't injected either the resource in the world and because I don't have access to read this resource from the world, which is this error over here tells me that I don't have access, invalid access. And so let's add access real quick. So let's tell it that this system can read from the resource U32. You either have this syntax to tell it to read that you can read from one resource, or you can just write the masks yourself like that. And this allows you to combine multiple masks as well. But yeah, we can just stick to the simple reads. That handles that stuff for you. Now if I were to run this, it would crash telling me that the resource is not present, which it isn't. So let's add it real quick. Let's come over here. Oh, I misspelled that. And let's just insert the resource. And let's just make it a value of 1, 2, 3. Very simple. If I were to run this, it runs and the value gets debugged as 1, 2, 3. As you can see, both those systems can still run in parallel, since system A for the dispatcher isn't reading or writing any resources, so it doesn't have any constraints. Now, I can tell it to read from the same resource, and that's fine because you can have as many readers as possible, and there's no problem with that. But the moment you tell it that you have to write to a resource, it's gonna have to split those two systems up. You can't run them in parallel, otherwise you're just gonna get a race condition. So I implemented the source system to basically avoid lock contentation whenever you're trying to read from multiple read-write locks in the world, which is how it's actually handled right now. It's just multiple read-write locks, because otherwise all the system would try to like read and write to their locks, and that really doesn't help. It'd be better if they were split up in these multiple threads and multiple groups. That way they execute sequentially for writes, but in parallel for reads. I actually have an example for that, and it's this ordering script over here. Actually, no, the wrong one. Is it single? Oh no, yeah, it's the ordering one. Right. So this actually handles complex ordering using these rules that I've set up. So some systems must execute after others and blah, blah, blah. So to run that example, you would see how some systems can execute in parallel. And that's because, all of them read and write to nothing, actually. This is actually just to test if the ordering system works. But yeah, as you can see, some systems can run in parallel, and some systems must execute after or before others due to their constraints. Now, for example, see this closure over here? This closure is, I'm pretty sure it's this one. This one that executes before, after user, because this other closure executes before user, and it's this one. So if I were to tell this closure over here, this system, that it writes to the resource U32, which doesn't exist in the world. The world is just completely empty for now. Or to tell it to do that, it would still be with the other ones because none of these read from such resource. For example, if I told system B to write to I32 instead, and system C, was it, to write to, I don't know, U8 instead, all these systems can execute in parallel because they all write to different resources. But the moment I tell a system to write or read, like it's mutually exclusive, to the same resource at the same time, it's gonna have to split them up into multiple sequential orderings, right? And this also supports, a thread count, so I could just tell a thread count of 1, which basically forces the whole system to run in single threaded mode. I don't know who would want that, but it's cool. So yeah, that was a little small demo of my dispatcher system. I haven't, as I said, I have no idea if I'm going to use it, but if you want to look for yourself, look at the code. It's pretty dumb, actually. This is the code that actually sourced the stuff. I have a bunch of comments because I had to implement this from scratch because I had no idea how to implement this, not gonna lie. The only thing I knew how to implement was the system's sorting, but any of the parallel stuff, I had no idea how to implement that. So I just made my own system that groups everything into groups, like over here. These are groups at their specific depths compared to the user node, which is a default node added automatically, and their read bits or mask and their write masks to help us differentiate from all of them. And this is the code that actually handles figuring out if you can merge you can merge a system within another group, basically. So that's what I'm doing. I'm just making it find the nearest group with the same depth and allowed read and write masks, so you can add that resource into it, or I mean that system into it. So yeah, hopefully you find that fun. It was fun to write, at least. Yeah, thank you.